All right, welcome to your last lesson for the day. We are going to talk about optimization, and I've assigned here a variety of optimization problems. This is one of those lessons that sometimes students remember really well, crush it in one day. Sometimes maybe we want to take it on to 2 days, so I will be asking for feedback a little bit on if you feel, you got through these optimization problems really well, we can keep moving on with Chapter 5, or if you want to spend a little bit of extra time next Monday. So if you feel strongly, you can email me first. Otherwise, look for a quizzes survey on Friday. Here. Now find the point on y squared x equals 2x closest to 1, 4. So remember, with optimization problems, you're always looking for a word that's about maximum, minimum, least, greatest, closest. You're looking for some sort of extreme value. And that's how you can tell it's an optimization problem. This will be really helpful when you're actually doing things like the AP test or even just a cumulative quiz, for me, is how to identify if it's an optimization problem or a related rates problem. So you're looking for things like these extreme value vocabulary. And then what you want to do, you're going to start off a little bit similar to what you would do with a related rates problem, meaning that you're going to start with your formula. Now, you might use some of your formulas from area, surface area, volume that we did before. A lot of these are also going to use distance formula, such as this one here, because we're looking about something that's closest, and that means that you want to find the smallest distance. So we're going to grab our old friend, the distance formula, right here. Now, what I'm looking at for this one is I am going to ask myself, how can I simplify this a little bit given the information that we have in this problem? Well, the first thing I'm going to do is I know that I'm going to use the numbers 1 and 4 for my x1 and my y1. The other thing I'm going to do, it just makes these problems a little bit simpler, is once I have an x and a y here, I'm going to drop the subscripts. All right, so now we've got a little bit neater. We still have multiple variables, and you're going to want to find the maximum or minimum, so you're going to be taking the derivative, and more variables means that you have to use implicit differentiation, all these other steps. I don't necessarily want to do that. What I want to do is reduce the number of variables, and then I won't have to use implicit differentiation. So the way that I'm going to reduce that here is I'm going to substitute for x or y because I want to keep distance, because I want to find the derivative about distance. So here I'm going to use my other piece of information, y squared equals 2x, and I'm just going to say, oh, well, that makes it easy to solve for x. X is 1/2 y squared. And now I only have two variables, a very normal amount, and so I'm going to take the derivative in terms of y, since that's the variable I have in my function here. And this is how you can tell it's not a related rates problem, because I'm just using the variable over here and not t. All right, so that derivative is pretty complicated. You're using the chain rule a lot. And so what I'd love to have you do now is pause here to make sure that you can differentiate this on your own. Pause the video and then come back and check your answer. Now, the reason that I'm leaving this all like this is since it's an optimization problem, the next thing that you're going to do is you want to set it equal to 0 because you're trying to find the max and min values. You're trying to find those critical points like we reviewed last week. And when you set a fraction equal to 0, you really are only setting the numerator equal to 0. You can multiply the denominator up, and that's going to make this a lot easier. So this becomes 2 times 1/2 y squared minus 1. I'm going to simplify that to just times y plus 2y minus 4, which becomes a much more straightforward problem to simplify by. We're going to distribute and simplify a little bit farther before we start solving, and I'm going to get that 0 is equal to y cubed minus 2y plus 2y minus 8 cancels out, so 0 is equal to y cubed minus 8. Now we're at the point that we can solve. We add 8 to both sides. Y cubed is equal to 8. So then y is equal to 2. Which makes sense if we look at the graph that we had here. So if our y value is 2, this would be the closest distance that we have between that point and this curve. Now, it does ask for the point, which means that you're going to have to answer as an ordered pair. Since I have the graph here, it's easy to see that the ordered pair would be 2, 2. If you didn't have the graph, what you can remember is y squared is equal to 2x. So then you can solve by plugging in the value here, and you end up with x equals 2 as well, meaning that the closest point, as I've said before, is 2, 2. Now, let's look at an optimization problem that's really common that requires a little bit more work with remembering some algebra skills. So here it asks, find the area of the largest rectangle that can be inscribed in a semicircle with radius r. So if I'm looking at this semicircle here, a rectangle inscribed would be like this. And now we want to find a way to have the area of the largest rectangle. So what that means is the thing that we are trying to optimize, the equation that we are ending up going to take the derivative of, is going to be our area of a rectangle, which in this case has a length of 2x and a height of y. Now, because the thing we want is going to be a prime, the rest of it we want to replace in terms of a radius r. So if I'm looking at this picture, I'm wondering how to translate x and y into r. Now, the first thing to remember is that this is of a semicircle. So the equation for a semicircle, or a circle in general, is x squared plus y squared equals r squared when centered around the origin, which this one is. Now, we want to solve for x and y in terms of r. So I'm going to start by solving for y given this equation, and I'm going to end up with y is equal to, subtract x over, so then r squared minus x squared, and this is the positive half of the circle, so it's the positive square root. So what that does is it tells us the value of y. So now we have solved for y, so we've reduced the number of variables here. If we want to plug in, we then get a is equal to 2x times root r squared minus x squared. And what we can do is we can actually take the derivative here in terms of x, because that's what we are ending up wanting to solve for, is where should we place this? R isn't actually a variable. R is a constant, like this. So treat R like a constant, and the rest of this is a product rule. So the derivative of 2, x is 2, and the derivative of root r squared minus x squared is 1 over 2 root r squared minus x squared times the derivative of the inside of that using the chain rule, which would be negative 2x squared, which I'm going to simplify to negative x squared over, oh, not x squared, I apologize. Let's get rid of that. Get rid of the x squared, root r squared minus x squared. So now when I take the derivative using the product rule, I get a prime is equal to 2 times root r squared minus x squared plus 2x times negative x over root r squared minus x squared. And now we are wanting to set everything equal to 0 because it's an optimization problem. And I'm also going to multiply everything by the radical denominator, root r squared minus x squared. And that gives us 0 is equal to 2 times r squared minus x squared minus 2x squared. Okay. So now we have this. We'll do a little bit of simplifying. We end up with 0 is equal to 2r squared minus 2x squared minus 2x squared. So then 0 is equal to 2r squared minus 4x squared. We want to solve for x, as I stated earlier. So I'm going to add 4x to both sides and end up with 4x squared is equal to 2r squared. X is equal to x squared is equal to r squared over 2. And so x is equal to r over root 2. Now, this is close to what we're solving for, but as it says here, you want to find the area of the largest rectangle there. So you're going to come back up here to this first number because you want to have an answer as an area. You now know that area is equal to 2x times root r squared minus x squared, and you know that x is equal to r over root 2. So you're just going to plug that into the formula and say 2 times r over root 2 times root r squared minus r over root 2 squared is going to be the area. Obviously, that is going to simplify down a lot, and you are going to end up with just r squared as the maximum area that this rectangle over here can be. All right, for our last example, here this is a very traditional, again, optimization problem. A cylindrical can must hold 1 liter of water. Find the dimensions that minimize the cost of the can. So minimize tells us it's an optimization problem. One thing that's really important here is you're talking about dimensions of something, but you have the unit here is liters. So what you will need to recall is that 1 liter is equal to 1,000 centimeters cubed, and that's going to be our conversion between dimensions and volume. So the volume is then equal to, a can is a cylinder, so pi r squared times h. We know that 1,000 centimeters cubed is the volume, and pi r squared h like that, where they're measured in centimeters. We want to minimize the cost of the can, and this is going to require a little bit of thought. Minimizing the cost of the can is the same as minimizing the surface area, because you're minimizing the amount of material. So surface area for a cylinder is 2 pi r squared plus 2 pi r h. Since we are going to want to minimize this, we want SA prime, or surface area prime. And we just want to reduce the number of variables here so that we don't have to use implicit differentiation. Now, the way I'm going to do that is I am just going to solve for h since it only appears once. I'll solve for h using this formula. So now I know that h is equal to 1,000 over pi r squared. I'll plug that in before I take the derivative. So surface area is equal to 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Obviously, there's a good amount of simplification that can happen with that second fraction. So what I'm going to do there is just change that into 2,000 over r. Now I will take the derivative in terms of r of both sides. So I end up with surface area prime is equal to 4 pi r minus 2,000 over r squared. And so you can do that using the quotient rule, or the way I thought of this as 2,000 times r to the -1 and use the power rule. Either way works just fine. The next thing I'll do is set this equal to 0 and multiply everything by the denominator. So r squared, 0 times r squared is 0. This becomes 4 pi r cubed minus 2,000. And from there I will solve by adding 2,000 over and dividing by 4. So 500 is equal to pi r cubed. Divide by pi and take the cube root. And obviously this is not going to work out nicely, and you're going to want to grab your calculator, so that the radius is equal to approximately 5.419 centimeters. And if we then plug that into our height function, the optimal height of this can is 10.839 centimeters. Let me know if you have any questions about optimization. Feel free to skip around back and forth, and I'll be in touch on Friday asking if you want an additional day on this topic. Expect to see a little bit of optimization on the quiz no matter what, but certainly not all the high-level problems that you will eventually